Hello everyone, welcome back. So let us continue our discussion. We are in lecture 4 of week 10 and this week our theme is torsion. Today we are going to learn how to model torsion with warping. Now all our earlier cases we considered either circular or non-uniform cross sections also we considered, but even for them we did not consider any warping, and the expression that we derived, if you recall, tau is equal to g r theta, right? Now this stress distribution is a linear function. As we have r equal to 0 on the right hand side, obviously tau equal to 0. And as we move away from the center of the shaft towards the periphery, our stress value increases and it is maximum at the surface. And that we have discussed and solved some problem, right? Today, we are going to learn, if we consider warping, how the expression changes and what are the modifications we need to do. And for that, let us consider shaft with any arbitrary section. Say this is the section, right? It has a center here and the longitudinal axis of the shaft we can mark using this z-axis. And at the section level, we have two more orthogonal coordinate system. This is our y and we have x. Now the length of the shaft is, say, z. Now we apply a torque at the ends. So let the torque at the ends be T, right? Let us use a different color to highlight that torque. So we have a torque applied T here. Similarly, this end also we have to apply the same torque. Now the moment we apply this torque, there is a rotation, and let theta be the rotation per unit length. Now, if we consider the section at Z, so here, and then let us consider a point here, let this point be P. Because we apply this torque, this point will rotate and will come to a new position, and let that position be P prime. And the rotation here is theta of Z. That means the rotation of the cross section of the point P at a distance Z from the left end, right? So what is theta Z? We can write it theta, that is the rotation per unit length, times the length, which is Z. Now before we move further, let us draw this cross section at the right side, this extreme end, and identify the displacement components, right? So for that, what we do, we first draw the cross section. So this is x, this is y. We actually look from this side and then draw this section. Now the section is defined by this boundary, and we have the point P here. So this is point P, it has a coordinate, say X and Y. And the distance of this point is R from the origin. Let this angle be beta. Now this point moves to a new position, which is P prime, and this angle is theta z, which is theta times z. Now from this geometry, we can find out the displacement along x and along y. So this is displacement along x, so we call it ux, and this is displacement along y, so we call it uy. Obviously, we can identify this angle also, and this angle is again beta. Okay. Now, what is ux? Ux is equal to minus r theta z. R theta z is here. Let me write it outside. So this is r theta z. So the x component is r theta z times sine beta. Now in place of theta z, we can write theta times z as per definition. That we'll do in a minute. But let us also identify uy. Uy is r theta z cos of beta. And let u z be theta times some function of x and y. And this is the warping function. Now carefully note how we define the warping function. It's not a function of z, it's a function of x and y only, right? Okay. Now let us also evaluate sine of beta. From the coordinates, what we get, sine of beta is y by r, and cos of beta is equal to x by r. So we can simplify the expression of ux. We have minus r. In place of theta z, we can write theta times z, and in place of sine beta, we can write y divided by r. So the r will be cancelled. So we are left with actually theta z times y. Similarly, uy, you can show that it is theta x z. And uz is theta times the warping function, which is a function of x and y. Now we have identified the displacement field ux, uy, uz. The moment we identify displacement field, if you recall our discussion on strain analysis, we can evaluate the strain components. So epsilon xx, which is derivative of ux with respect to x. And if you look at the expression here, our ux for this arbitrary cross section is 0, because it's not a function of x. So if we differentiate that with respect to x, we'll get 0. Similarly, if we find out epsilon yy, we again have 0, because the displacement field along y, it's not a function of y, and therefore we'll get 0. What about epsilon zz? As per our definition here, it is theta, that is the rotation, times a function which is called the warping function, and that's not a function of z. So if we find out this quantity, obviously again it will be 0. Now, what about gamma xy? As per definition, we can find it out from the ux and uy. Now, if you look at uy, it is theta times x times z. So if we differentiate with respect to x, we have theta times z. And ux is minus theta times z times y. If we differentiate that with respect to y, we'll have minus theta times z. So effectively, we'll have 0. Now, let us find out the other two strain components, and then we will see what is the property of this warping function. So, the other two components of strain, first one is gamma yz, and gamma yz is now this we can find out from the expression of uy, which is x theta z, and uz, which is theta times psi x comma y. So the first one, uz with respect to y, we have to differentiate. If we do that, we have theta times the warping function differentiated with respect to y, plus, if you recall uy, it is theta times x times z. So if we differentiate that, we'll have theta times x. So effectively we get theta within bracket right. Similarly, we can also find out the last remaining strain, gamma xz. Gamma xz, if you recall the expression, is uz differentiated with respect to x plus ux differentiated with respect to z. Now, the expression of uz is theta times psi function. So, we have theta times psi differentiated with respect to x plus ux is actually minus theta times yz, right? So, if we differentiate with respect to z, we'll have minus theta times y. So, effectively we have theta within bracket psi differentiated with respect to x minus y. So, we get all the strain components, and then we can also find out the stress components, right? Now, recall sigma xx, it is, if you recall, related to sigma yy, sigma xx, sigma yy, and sigma zz. All of them are 0. So, it is 0, and for the same logic, sigma yy, sigma zz, they all are 0. Not only that, tau xy, which is gamma times g, because gamma xy is 0, so this component is also 0. So effectively we have two shear stresses, tau yz, and that is g times gamma yz. So in place of gamma yz, we can now write the expression that we have just derived. So that is theta times differential of psi with respect to y plus x. Similarly, we can also write down the expression for tau xz, which is g times gamma xz. And in place of gamma xz, we can write the expression that we have derived here. So let us complete that exercise. So we have theta times right. Now we have all the stress and strain components, right? Okay. Now, before we move further, let us first satisfy the equilibrium conditions. So if you recall the equilibrium condition or equilibrium equation, we should say. So we have sigma xx differentiated with respect to x plus tau xy differentiated with respect to y plus tau xz differentiated with respect to z is equal to 0. Obviously, we do not consider the body force. Then the second equation, tau xy differentiated with respect to x plus sigma yy differentiated with respect to y plus tau yz differentiated with respect to z, this is equal to 0. And the last equation, tau xz differentiated with respect to x plus tau yz differentiated with respect to y plus sigma zz differentiated with respect to z is equal to 0. Now, recall we have just derived sigma xx is 0, tau xy is 0. As you can see here. Now, if you look at the expression of tau xz, which is here, you see this is not a function of z. Therefore, if you differentiate this expression with respect to z, it will be again 0. So, this entire quantity is 0 because tau xz is not a function of z. So, the first equation is satisfied. What about the second equation? Again, tau xy is 0, sigma yy is 0, and then tau xz, we have the expression for tau yz. Tau yz, again, it is not a function of z. So, if we differentiate this with respect to z, this component will be 0. So, the second equilibrium equation is also satisfied. Now, what about the third equilibrium equation? Sigma zz is 0, but the remaining two components, tau xz and tau yz, they are non-zero. And if you look at the expression tau xz is here. So, we can differentiate this expression with respect to x because we have psi function which is a function of x and y. So, we can differentiate that. Similarly, tau yz, we can differentiate with respect to y, and then we can see the condition that we get. So, for this last equation, we have the first term where tau xz is differentiated with respect to x. So, for tau xz, we can write g theta times psi differentiated with respect to x minus y plus the second term, in place of tau yz, we can write g theta times now if we simplify this expression, what we get, g theta times second term will be 0 if you open this first bracket, plus we have g theta so ultimately we get g theta times now obviously g theta, their positive values, they are not equal to 0, so we are left with so this is the first important expression. So for the warping function is concerned, warping function must satisfy this equation. This is the Laplace equation. So warping function, which is a function of x and y, it must satisfy the Laplace equation within the cross section, within the domain. Here if you can see, the domain is defined by this coordinate system. Over this, within this domain, it must satisfy this important criteria. So we get the first important equation. So for the warping of the section, arbitrary section is concerned. So this is the most important relation. Okay, now let us continue further. Let us also write down the expression of Hooke's law in 3D. If you recall the Hooke's law, we had sigma xx is equal to nu e divided by 1 plus nu times 1 minus 2 nu times delta plus e by 1 plus nu times epsilon xx. Similarly, we can also write down epsilon yy and the last one is epsilon zz. Then for the shear stresses, we have tau xy is equal to g times gamma xy, tau yz is equal to g times gamma yz, and tau xz is equal to g times gamma xz. So we have used these two relations in the previous slide. Now I will draw your attention here. Just look at the values, because we have the stress and strain components are 0. So if you put that values, just see what is the ultimate conclusion you have, and that I just leave it as an exercise for you. Okay. Now, if you look at the arbitrary cross section that we have considered, we have already satisfied the equilibrium condition, right? And that's how we derive the expression for Laplace equation. Now, let us quickly draw the cross section once more. And what we'll do now, we'll satisfy the fractions at the surface, and we'll see what we get. Let us quickly draw the cross section. That is the cross section. And let us consider a small element here at the boundary, right? So this is the small element we consider at the boundary. And at this element, we can define the outward normal N, and we can define the forces Fx, Fy, Fz. If you recall, the first expression that we derived is Nx times sigma xx plus Ny times tau xy plus Nz times tau xz is equal to f of x. Similarly, we have Nx times tau xy plus Ny times sigma yy plus Nz times tau yz is equal to fy. And the last one is Nx times tau xz plus Ny times tau yz plus Nz times sigma zz is equal to f. Now, let us draw this triangular section and draw the free body. So we have this is the section, and if you look at the coordinates, we have minus delta x here, then delta y there, and this one say delta s. So we have the outward normal N. Okay. Now, look at the components of the streams which we have already derived, and for that again let us mark. So sigma xx, this component is 0, tau xy, this component is 0, and then nz for this wedge is also 0. So we have here nx, ny and 0, because z coordinate is perpendicular to this plane, and this plane we have identified here delta s, it makes 0 angle, and therefore nz is 0. Similarly, tau xy is 0, sigma yy is 0, and nz is 0. Therefore, we have fx is 0, fy is 0, which is obvious because we do not apply any force along x and y, we only apply torsion, which is along z axis. If you recall the first diagram where we identified the external forces, and as you can see this green mark, double arrow, so it is in the z direction. No other forces are acting at the boundary. Now let us look at the last equation. Obviously, fz is equal to 0 due to the same logic, and in the equation we have nz0 and sigma z0, right? So we get now another condition. We have nx tau xz plus ny tau yz is equal to 0. So this is the condition at the boundary that we have to further investigate. Now from this diagram, what you can see, what is nx? Nx is dy ds, and ny is equal to minus dx ds. So effectively what we get? We get in place of nx we have dy ds, and tau xz we can write down the expression that we have derived. It is here. So g theta times derivative of psi with respect to x minus y. Right. So let us write down the first expression. So we have g theta and in place of nx we can write dy dx plus second term again we have g theta, then tau yz. For tau yz we have the expression here, and let us put that expression, right? So we have and in place of ny we can write minus dx ds. This is equal to 0. So we get another important condition, and that is this is equal to 0. So the first condition we get the Laplace equation that psi of xy must satisfy. Also this condition, it must satisfy at the boundary. So psi of x comma y must satisfy this condition, and this is defined at the boundary, right? Okay. Now let us also find out the force at the section level. So we are at the extreme right face here, and at over this face we have only capital T, that is the torque applied. And at the boundary we have identified that fx, fy, fz is 0. But over the domain, if we can find out what is the net force in x direction and net force in y direction, let us see. Intuitively we can say that both of them must be equal to 0, because we do not apply any net force over this region, say R, along x and along y. It is satisfied over the boundary, but let us see what happens if we find out the total force along x direction and y directions over this cross section, right? So let us do that. For that, what we do? We again consider this cross section, and here let us consider a small element of size dx dy. Now what are the stresses acting here? We have two stress component, tau xz and tau yz. So let us first consider x direction. So we have tau xz over the area of dx dy, and if we integrate that function over the domain, we get the net force acting, say fx. We just put subscript r just to differentiate this with the fx at the boundary what we have here, right? Okay. So this is the net force that we derive from the stress acting over the region, the cross section that we have just identified. Now in place of tau xz, we can write it expression. So we have g theta right? So what we do, we just put the expression of tau xz and then we get this expression, right? Now we can slightly modify this. Just carefully note how we are going to modify this expression. So we have g theta, then the first part I leave it as is, plus I introduce a new term x times the Laplace equation. Recall this part is 0 and therefore we do not add any extra term. We simply modify the original expression here within the double integral, and now we have this expression. Now this expression further we can simplify. Then we have g theta here. We can write so we have here x times right. Now you can see this is a surface integral over the surface defined by this R, and what we are doing, we consider this small segment and then first find out what is the elemental force over this segment along x direction, and then we integrate over that complete surface. Now here we can actually apply Gauss theorem, and then instead of this surface integral we can actually convert it into a line integral, and if we do that, so it is over the boundary, and then this expression is equal to the function here within third bracket. So we have x times nx. Nx is basically the direction cosine, plus we have x times so what we do, we apply Gauss theorem. So what we can do, we can take this x common because that is the common component. So what we can write is x within third bracket we have, in place of nx we can write dy ds, plus we have the second term and in place of ny we can write minus dx ds. We have a third bracket here actually. Now you can see the condition here we have derived. The third bracketed term here, it is equal to 0, right? That is the condition, second condition that the warping function must satisfy. If that is the case, what we get here if xr is equal to 0. Right. So this is another important thing, and it actually satisfies the physics because we never applied any resultant force at the end except the torsion. So over this section, we never applied any force along x direction except this torsion here, capital T. And that is what we get from the derivation here. Similarly, we can also prove following the same derivation if YR is also equal to 0. Right. For that, what we have to do? We have to consider tau YZ acting over the small area. So here over the small area, if we consider tau YZ, then we get the net resultant force acting along y direction. And if you follow the same route, you will get again the same condition, apply Gauss theorem, and you can prove that this resultant force along y direction is also 0. So what we are left with? We are left with the torque that we apply, and let us also quantify the torque, right? So at the extreme ends, we apply this torque capital T that we can quantify. For that, what we have to do? Again, we consider this differential area, and from that we can actually find out what is the net torque applied. So let us do that. So applied torque T is equal to tau of yz times dx dy. So this is the force tau yz times dx dy. It is along y. So that multiplied by x is the torque minus, because the other one is acting, producing a torque in the reverse direction. So we have tau xz or zx times dx dy times y. So we have to integrate this expression over the entire domain. What we can do, we can put the expression of tau xz and tau yz, that we'll do in a minute. So we have the net expression tau yz times x minus tau xz times y dx dy. Now let us put the expression of tau yz. It is g theta times x times yz is equal to differential of psi with respect to y plus x minus, again we have g theta times y, and xz is differential of psi with respect to x minus y. So we can simplify further. G theta is constant. It will come out of the integral. So we have x square plus, we have y square here. So x square, y square. Then the first term, x times differential of psi with respect to y. Then minus y differential of psi with respect to x times dx dy. Right. So now you can easily identify the term here within this double integral, and this is nothing but the polar moment of inertia J or IP, whichever way you call it, Probably we used IP earlier. So G theta times IP. What is IP? IP is equal to double integral x square plus y square plus x dou psi dou y minus y Now, important thing to be noted here is that if we have no warping, obviously these two components will vanish and we'll be left with double integral x square plus y square dx dy, which is the polar moment of inertia if you do not have any warping. So if you have any arbitrary function, now we can find out the polar moment of inertia where we'll have these correction terms, as you can see, due to warping of the section, right? If you recall, for a circular shaft without warping, we use this x square y plus y square dx dy. This is the expression we use to find out polar moment of inertia, right? So we have only one correction arising because of warping. Otherwise, the expression that we get T is equal to G theta IP is again the same that we derived earlier, right? Okay. Now let us take an example. Let psi of x comma y is equal to c. That means warping function is constant, right, over the cross section. So recall the second condition. So on the boundary, we have the expression this is equal to 0. This is the second condition that we have derived, right? Okay, now if we have this special case where we have warping function is constant, then what we get? The first term will be 0 minus y dy ds plus, again we have the first term here in the second term, the first term differential of psi with respect to y is 0. Then we have minus x dx ds. This is equal to 0. So effectively what we get? We get d ds of x square plus y square by 2 is equal to 0. So what we get? X square plus y square is equal to constant. So this defines the boundary. And what is the geometry? It is the boundary of a circle. So if we have warping function is constant, then the boundary that we get is actually the circular shaft, right? Now, what is uz? uz in this case, if you recall, theta times psi of x comma y, right? So we have theta c. What is IP? IP is equal to double integral x square plus y square dx dy. Because psi of xy is constant, so if we go back to the general expression, obviously this term here and this term here, they will vanish, and effectively we will be left with x square plus y square times dx dy. So what we get, theta or t is equal to g theta ip. From this expression we can find out theta is equal to t by g ip. So what is uz? In place of theta we can write t times the constant c divided by g ip, right? Okay, now let us find out the stress. Tau of yz is equal to g of theta times x. So what we get here is tx divided by ip. Similarly, tau xz is equal to minus g theta y, right? And for that we have minus ty divided by ip. Now what is the resultant stress? Tau r square is equal to tau xz square plus tau yz square. Now if we put the expression of tau xz and tau yz, you will get t times x square plus actually t square y square divided by I p square. So effectively what you get, tau r is equal to t times square root of x square y square. So if we look at the cross section, so at this point, say we have x comma y, recall the point P, this distance is r, so r is square root of x square plus y square. So what we get here, square root of x square y square, so that we can replace with r divided by I. So again we get the same expression that we derived in the previous lectures for circular cross section. So that tells that our assumption, first this condition is okay because that leads to the condition here which gives us the boundary of a circle, and for a circle if we consider psi of xy to be constant, then we again get the same expression that we derived earlier. So that concludes the derivation. If we have warping now, you can actually consider any arbitrary section. For that, we first have to solve the Laplace equation that will give the warping function, and we have to satisfy this additional condition here, the second condition over the boundary, and then we'll get the solution psi of x comma y, and the moment we get that functional form, and then we can find out the polar moment of inertia from the expression we have derived here. So this is the polar moment of inertia. Using this expression, you find out polar moment of inertia, and then from the displacement field, you can easily find out the strain and stress, and you can also find out the resultant stress. And as you keep on changing x and y, we can also find out the stress profile over the cross section when we consider arbitrary section and warping. So go through these derivations, and if you have any doubt, do let us know. We'll clear your doubt. With that, let us conclude our discussion on torsion. We'll move over to the next topic in the following week, and that will be energy principles, right? Thank you very much.